I'm going to talk to you today about grapheme to phoneme conversion, which might not be the NLP application you hear about the most, but it's a fairly important one if you're doing any sort of speech application. So the general idea is that you have representation of orthography, spelling, just normal text. And what you actually want to have is a representation of the pronunciation, a representation of the sound, not like a waveform or anything, but like a sequence of phonemes, basically. And the goal is to figure out the relationship there, which usually isn't such a difficult problem because in most languages there is some known relationship between the writing system and pronunciation, with one notable exception shown on that slide there. The other notable exception being Chinese. But the problem, of course, as you often face in NLP, is that what works well when you have a lot of data for a couple of languages that everybody writes papers about, things work quite well. But when you move beyond those to the long tail of languages, you are in a lot of trouble because old-fashioned rule-based systems, sure, you don't need data for them, but you do need expertise, which you're probably not going to find, and those things don't work so great anyway. The other issue is that if you're working with any sort of statistical or neural system from recent years, you're probably going to need more data than you have. And this seems like a pretty intractable problem, except for this one crazy idea, which is, why not just train one system for all of the languages in the world? And so the thing about writing systems is that they are pretty similar to each other. The mappings are similar, not identical, and a fairly small number of scripts will cover basically all the languages you want to work with. Spelling rules are similar, not identical cross-linguistically. So for example, with the string real, real, there's a variety of different pronunciations in these languages that I dredged up, but they're all like clearly in certain ways related to each other. So perhaps we could solve the data sparsity problem by training all these languages together. However, until recently, there weren't really such good ideas to make use of this because there's nothing in the representation there that indicates to you, for example, that the various different R phonemes are relevantly similar to each other. But anyway, the innovation is to solve it with a sequence-to-sequence model. Specifically, and the reason I'm here, I guess, is that it was a sequence-to-sequence model implemented in OpenNMT-Pi, basically with generic hyperparameters. I found that there wasn't really any problem at all using smaller embeddings or smaller hidden layers. And I suppose because my data set was rather small, but I'm not sure about that. It was also very helpful that I could use something small because at the beginning I was training on the CPU and I didn't want to kill my computer. So naturally the problem's completely character level. Using a bidirectional LSTM encoder was quite important. There's global attention, naturally. Basically, again, just the default recurrent neural network machine translation. And the key point is that your grapheme embeddings are shared across all languages, and your phoneme embeddings are shared across all languages, and the encoder and the decoder and the attention mechanism are shared across all languages, allowing the model perhaps to learn the useful linguistic similarities. Then you add some sort of representation to indicate what language any given sample is in. You could use either just a simple fake grapheme on the source side, which tells you what language it is. That's similar to what Google did for their zero-shot system. The other thing you could do is by concatenating a source feature that tells you what language you're in. The two approaches work more or less similarly, although I found that the features usually work a little bit better. So I found a data set for this task from a couple of years ago, an approach that was quite similar, except they did not use anything neural. They collected spelling pronunciation pairs in hundreds of languages, and then what they did is that for the high resource languages, they trained weighted finite state transducers, and then they used a system of computing the distances between languages based on typological factors and the differences between phonemes similarly in order to adapt a high resource model for a low resource language. So comparing their results to mine, it was useful to use these basically standard error metrics for the task. The phoneme error rate is just the normalized Laifenstein distance. the word error rate, how often was the model's guess not exactly correct? Word error rate at 100, how often were the model's first 100 guesses? How often were none of them correct? And so on, averaging the metrics across all languages. And so the results are way ahead of the weighted finite state transducers. They might not look so impressive because a small number is good here, but one must consider that the median number of training samples for any language here, I believe, was less than 200. That's the comparison to the non-neural baseline compared to monolingually trained networks. I didn't make them for all of the languages, but I made them for more than 80 of them. And you can see a pretty clear relationship that for the languages for which you do not have a whole lot of data, the phoneme error rate was much, much better with the multilingually trained model than with the monolingually trained one. It's also interesting to have a look at what exactly was learned by the parameters of the language. So, for example, you could look at the grapheme embedding space. That might not come through so well here. But there's a very clear trend that graphemes from different writing systems are located closely to each other if they tend to represent similar sounds. So you have the M, which is located close to the Greek mu and the Arabic meme, and so on. Similar things are played throughout the space, and on the target side, you can see a similar thing, where there is very clear clustering among similar but not identical phonemes. These were t-SNE plots, so there's a little grain of salt, but I ran a whole lot of t-SNEs to try to find, if the thing was consistent, and this did keep on showing up. It's interesting also to see, just if you give the model the same string but with different language identifiers, what sort of variation it learns. So the string JUICE, juice in English, contains J and C, which are both very high entropy characters. They tend to be used in different ways in different languages, and one can see from what it produced when it was told that that was a string of different languages, it produced different things. So it sees juice, but German it says jutze, and it sees juice, but it's Spanish, and it produces juice, which is generally more or less what you would expect if you were going to apply the pronunciation rules of those languages to that string. There's even something fairly reasonable for Arabic, which is interesting because for Arabic there were no training samples in the Latin alphabet, which could have an interesting future application if you wanted to make use of the cross-script character embeddings learned by this model here. But anyway, there's certainly many things to do in the future. For example, the models, the data cleaning for the data I had was somewhat lacking in some ways, naively replacing phonemes which it decided not belong with ones that were similar by various phonetic factors, but that did not account for how things work in the real world. So for example, there were a bunch of German transcriptions containing the upside down lowercase r phoneme, which is an English R, and the cleaning algorithm knew to replace that with the closest sound by Hamming distance between the phoneme feature vector from the Foible database that did belong to German's orthography. The problem was that there was a tie between an R and an L, and it picked the L, which is not ideal behavior in the case of German. There are various things I could talk about offline later for ideas to clean data better. So there's also the issue that the performance for low resource languages still naturally lags far behind that for languages where you have lots of data. One sort of cherry-picked case is there's a lot of data in my corpus in Serbo-Croat Bosnian, which has an extremely regular writing system. But then there's also a bunch of data that's labeled just Serbian or just Croat or just Bosnian, which will use the same systems of orthography essentially and the same phonemes, but the results are way worse for the Serbian, Croat, and Bosnian data. A possibility would be to use linguistic knowledge as an alternate input. There was a paper about that sort of a couple of years ago involving using data from typological databases as an alternate input to a phoneme level recurrent language model. Certainly there are a bunch of other ideas too, because a plain sequence-to-sequence model isn't necessarily making the best assumptions for the task. I'm producing IPA in several different languages here, and even though you might not think that softmax is a problem the way it often is, softmax of course often a problem because you have a large output vocabulary. In my case, the output vocabulary is very small, but even so, the thing is trained multilingually, and for any given language, the vast majority of the possible phonemes are a priori impossible, and the model doesn't include any architecture that allows it to make use of that fact. The other thing in graphing to phoneme conversion, the alignments are mostly monotonic between the source and the target strings. Perhaps you could make use of local attention to do that better. Another idea, of course, would be to jointly learn phoneme to grapheme, which would allow you to double the amount of training data you have and enable zero-shot transliteration, where sort of you have sort of your pivot is the IPA representation, I guess. And thanks. Questions?
It makes me so happy that we had at least one slide that used the word linguistic in this whole. Any other questions? Yeah.
Hi, thank you for your presentation. So instead of predicting IPA, if we change the problem into ARPA character prediction, maybe, and then it could be like the classes will be smaller, and maybe that could be something you could try.
So if I am correct about ARPA, it's just another phoneme representation, but specifically for American English, right?
Not necessarily, but it can be also, there are other like European notations for European languages, like a SAMPA system or ARPA system, but they're simpler than IPA system. So it could be, if you do some post-processing.
I mean, if I think that your representation in ARPA or SAMPA or whatever will end up being basically isomorphic to the IPA you have. And I have a corpus in IPA, and I find IPA much easier to read than ARPA. So that sort of guided my decision making there.